And a few words about another exploratory multivariate method that can also be very helpful in some research situations. It is called multidimensional scaling. Just like cluster analysis, it also allows us to explore and visualize our data. And just like cluster analysis, it is also based on a distance matrix. And there are different ways to compute those distances, just like in cluster analysis. So there are many similarities. But unlike cluster analysis, which tries to join individuals or variables into groups, multidimensional scaling tries to identify dimensions that would optimally explain these distances. So essentially, it's something in between factor analysis and cluster analysis. But of course, if you apply it to data to which factor analysis can be applied, the results that you will get will be very similar to what you get in principal component analysis, because multidimensional scaling is essentially a very similar method. But the real power of multidimensional scaling is unleashed in situations when you have some non-normal data or non-metric data, or even some results of pairwise comparisons, some similarity or dissimilarity matrices. And there, exploratory factor analysis basically is not going to work at all. And also sometimes we have very different, very difficult data structures where exploratory factor analysis has problems. So for those situations, either cluster analysis or multidimensional scaling can save the day. I will not go into many details about multidimensional scaling. In SPSS, there is a very good module on MDS, much better than on cluster analysis, in fact. There are different algorithms. The most advanced and modern one is called ProxScal, which I recommend you to use. And it can even work with several matrices with a 3D data matrix. But in most cases, we just have one matrix and we tell it to create proximities from the data. Proximities are basically the inverse of distances. So we can say other options, other types of multidimensional scaling, they use distances. This ProxScal use proximities, but in fact it's just inverse. And we add all of our variables, and with all the default settings, Euclidean distances and no standardization, and default initial configuration, we get this nice picture, which is a two-dimensional representation of relationships between our emotional variables that we have just analyzed. As a measure of fit, we can take a look at this stress index. If it's below 0.10, it's good. And then we use the same approach to interpret the meaning of these dimensions as we used in factor analysis. We check out which variables have high and low scores on each of these dimensions. So for dimension 1, it's fairly straightforward that all the negative emotions are on the right and all the positive emotions are on the left. But for the second dimension, it's a little bit more tricky. Because to interpret it, we need to ask a question: what is common for ashamed, guilty, proud, and inspired, and nervous on the one hand, and what makes them different from irritable, upset, distressed, active, attentive here on the other hand? So maybe it makes no sense really. Or maybe these are more related to some social interaction, and these are maybe more related to some internal states. So different interpretations can be possible. In this data set, actually, this second dimension is not supposed to happen even. That's why it's not very meaningful. But in some cases, you will see a very meaningful structure here. And then it's a good idea to apply multidimensional scaling. And there are many examples in psychology of very interesting applications of multidimensional scaling. For example, this model of values by Shalom Schwartz, which was essentially created using multidimensional scaling. It works well in situations when the structure of variables is either hierarchical or there is some kind of additional organization. For example, circumplex. In a circumplex, variables in a two-dimensional space, they are located in circle, just like those values in Schwarz's model. And in this situation, exploratory factor analysis will give you a very strange factor loading matrix. Of course, if you plot factor loadings, you will see this circumplex. But just based on factor loadings in the table, it's very hard to get an idea of what's in there. And rotation can screw it up quite strongly. So multidimensional scaling is a much better way to identify structures like this. Of course, the problem here is that it's somewhat dependent on initial configuration. So by changing default initial configuration, you can arrive at slightly different models, especially if there is no clear structure in your data or you have too many dimensions, then your model will be very unstable. So in addition to just this measure of stress, we need to look for stability of this model against different initial configuration. And the main criterion is, does this model really make sense? Is this interpretable? And in Schwarz's model, there are two dimensions, self-transcendence on the one hand, self-enhancement on the other hand, and openness conservation. And of course, this model is supposed to replicate in different samples. And this is what we see for Shalom Schwarz's model. It's been replicated so many times, the same dimensions, always using different questions in different cultures. And that makes it a very good model, even though it's based on multidimensional scaling, which is a very uncommon method. Okay,